Okay, in this problem, we're going to look at how to find eigenvalues again, this time for a 3 by 3 matrix. So in the last video, we can go ahead and simplify this a minus lambda I down to this on the main diagonal. Remember, just subtract lambda, which is the eigenvalue, from each entry on that diagonal, and then leave all of the other entries alone. All right. So the determinant of this matrix is, let's see, I've got negative lambda squared. I'm using the diagonal rule again, times 8 minus lambda, plus 4 plus 0, minus 0, minus 17 lambda, minus 0. So this, I'm going to clean this up a little bit, but that is, we want that to be equal to 0. And so this is going to be 8 lambda squared minus lambda cubed plus 4 minus 17 lambda. What I'm going to do is I'm going to rewrite this so that the powers of lambda descend. And also I'm going to multiply by negative 1 to get the leading coefficient to be positive. So that's the equation that I have to solve. And if you remember from the last video, not only was it an easier problem because it was a quadratic, but as it turned out, it was already factored for us. Notice that this one is a cubic, so in general, that would be harder than a quadratic. And also, it's not factored already. So we just have to use the techniques that we would use when factoring a polynomial in general. So remember, this being a 1 and this being a 4, again, whether it's 4 or negative 4, it doesn't really matter, but that means that the only possible rational zeros are plus or minus 1, plus or minus 2, and plus or minus 4. And we can check and see that 1 and negative 1, there are easy checks to see that those don't work. Remember, 1 would be a 0 if all the coefficients added up to 0, which does not happen here. And negative 1 would be a solution if the odd powers coefficients added up to the same thing that the even powers coefficients added up to. So 1 plus 17 is not the same thing as negative 8 plus negative 4. In addition, we could use Descartes' rule of signs to say that because the signs alternate, there are either 3 positive roots or 1 positive root and 1 negative. Or sorry, 1 positive root and 2 imaginary. So we don't even have to check negatives. We could check 2, but just really quickly, 2 cubed is 8, minus 8 times 2 squared is minus 32. Which is negative 24, plus 34 would be 10, minus 4 would be 6, so 2 does not work. And then if we checked 4, 4 cubed is 64, minus 8 times 4 squared would be minus 128. That's negative 64. Plus 68 would be 4, minus 4 would be 0. So 4 does in fact work, and I'll just run that through synthetically to see what I'm left with. All right. So that means that this is lambda minus 4 times, and here's what we're left with, so lambda squared minus 4 lambda plus 1. This thing does not have integer solutions, but it's a quadratic, so we can use quadratic formula. And so we get lambda equals 4 or lambda equals, and now I'll just use quadratic formula. So negative b plus or minus the square root of b squared minus 4ac all over 2a. And then that's 4 plus or minus, this is square root of 12, so 2 root 3 divided by 2. And when we simplify that, we get 2 plus or minus root 3. So again, as I said in the last video, because this is 3 by 3, the matrix, that means I could have at most 3 different eigenvalues. And in fact, I do have three different eigenvalues on this. I have 4, I have 2 plus root 3, and I have 2 minus root 3. Now, I'm not going to ask you to do a 4 by 4 matrix, but the idea is the same. You should get a 4th degree polynomial at this point. Whether it's factored or not just depends on the matrix, but you'll eventually have to try to factor it to come up with those solutions, and you would go about it the same way. So hopefully that makes sense, and if you have any questions, please let me know.